Today I'm gonna try to do this slightly differently, so we're not gonna be making, well, actually I think I will have a few questions thrown in the open, but we won't be making a kind of a discovery journey. We will be making a journey with a lot of stops. So we're gonna be dealing with noise, and well, I have collected, what is this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 types of noise we could generate. And I have 1, 2, 3, 4, 5, 6 kind of modulation targets. That's 60, that's 2 minutes for each of the combinations. So obviously we won't go through all the combinations. But we will talk about all these targets. Essentially, the targets are not so interesting, I think, to discuss, because that's something you discover yourself. That's more of a musical application. But in terms of the types of noise we can generate and how we do that, we will mostly focus on this bit. Now, the thing is that I've discovered today, as I was testing around and picking modules for tonight, I discovered that my actual white noise generator is everything but white. It's broken. I've put it into the broken bin. We can have a look if you like. It might be just replacing an IC or something, because the level has dropped significantly and there's no mid frequencies. There's a lot of high frequency in there only, so it's nothing like white noise. So we won't be basing anything on white noise, and actually the generator that also has colored noise. So let's first just discuss this thing about noise and the color. So white noise, you probably know, flat spectrum. On a linear scale, not on a log-log scale, so not as we hear it. That's why we have the pink noise, which is flat on a log scale. That's why the pink noise sounds more flat to us than white noise. Yeah, so white noise sounds a bit top-heavy. So the point about noise is that it's a broadband signal, and it would, if it's a pink noise, it would have equal amount of energy per musical interval, you could say per octave or anything similar, whereas white noise would have equal amount of energy per hertz. And that's why we have this kind of log linear scale discrepancy there. The thing is that synthesizing pink noise is a bit of a holy grail for engineers and programmers. You can find papers that go into, you know, 1 dB accuracy over 20 octaves, 1 dB accuracy over 30. I don't follow these things. I don't quite know what the detail of this progress is. But in any case, it is a difficult task to synthesize this. So you understand that obviously if I say, okay, white noise is top heavy, pink noise is kind of flat, brown noise is bottom heavy in terms of frequencies we hear. So you could say, well, yeah, it means that I can manipulate this color of noise with a filter. The thing is that if I want to have pink noise from white noise, I believe it's 3 dB per octave, might be 6, of continuous slope. And that's the problem with producing it, because with a filter, you would have a cutoff point, and then you get a kind of a reliable slope. But when you want to synthesize these noises accurately, then you really need a continuous slope over a very large range. So that's the story. Actually, we have ordered, it's been a month, from SSF. They have this rainbow called module, which has, I think, 8 colors of noise. But they have a problem at the factory. I don't know, it hasn't been shipped yet, so we can't look at this. But instead what we will be looking at is essentially triggering noise value. So the only noise generator I have here, which should be sufficient for what we are trying to do, is what they called quantized random voltages generator. And what this does is it produces essentially a stepwise noise when you give it a trigger. Yeah? So I'm going to trigger that with a pulse wave. And for each trigger, we will get a new random value. Yeah? So it's worth saying that in digital systems, white noise is generated by synthesizing a random value, uniform distribution random value for each digital sample, and that is white noise. Brown noise you can synthesize essentially by having a random process which steps away from the previous sample value. which has to do with Brownian motion. I don't know if you know about this. Okay, so what I'm going to do now, I'm going to be triggering my little quantized noise generator. First of all, this is my pulse. That looks a bit funny, 5 volts. Okay, that's a sine wave. Let's get this pulse into focus here. Yeah, so that's my pulse wave. Maybe I should trigger it as well so we see it fixed. Channel 1. Okay, that's the pulse wave. And then if I use that pulse wave to trigger my quantized random voltages, I should get something out of that. Don't tell me I broke it in the... Looks like it's doing things. Here we are. Okay, so you see you get a kind of a stepwise function from that. See? Now obviously if I increase the frequency, that will increase as well the regularity or the density of these steps. So what I'm going to do as well now is I'm going to listen to this signal, and well, obviously careful because it's more of a CV voltage than an actual audio signal. Let's see, would that do something? Okay, so I'm going to increase the frequency. Here we go. Okay, so we're still looking at this random stepwise signal. Okay, now we could ask how far up in frequency we can go. Can we actually generate white noise from this? And this is my oscillator at its highest, which is really high. That is 11K. Actually, maybe I could try it with this one. What would this one give us? This one gives us 3.2K, so not even close. Okay. What I can also try, it's worth. Sorry for the discomfort. What I can also try is make put in a DC signal, yeah, into the CV control of the oscillator to get out of the range which is available through the dial. We've seen this many times, and almost every module will have a limited range in terms of controlling it with the dial. And if it has a CV input as well, if you really burn the CV input, go plus 12, minus 12, you can normally get beyond the range that is actually available through just the dial. So let's see if we're lucky with this one. So I'm getting into the CV in here. There we go. Yeah. So you see, with the dial I couldn't go as high in the frequency, but with this, well, that's 26K. Yeah. And now I'm only putting in plus 5 volts. This is my max plus 5. If you remember from the first class, my hack to make plus 12, probably go up to 30K, 50K, whatever. You remember my filter went up to 60K like this, yeah? So that's really useful to know that, you know, you can burn your modules way be out of their range if you have these DC signals in the CV input. And to be honest with you, I think it's going to be my next project. We can try to make this together. You know, just a DC generator that actually gives me minus 12, plus 12 on a pot. You know, it is a really handy kind of thing if you want to do these things. How do you like this sound? Where's the cat actually? Yeah. It's not reacting? Come on.
See the ears moving.
You see the ears moving? Yeah. Exciting noise. Okay, so actually now that we have this, let's hear what happens to my noise at these frequencies, hopefully. Okay, what am I doing here? Oh yeah, it was this one that seemed to work. And then, hello, what's going on? Pulse, okay, pulse is there, and then the noise is kind of there as well. Oh yes, and then my listening cable should be this one. Okay, So we get this noise, and now with the DC, you see I've actually made it. Yeah, so you see what's happening as I increase the frequency. So I'm going to go kind of slowly from low to high. Yeah, so you've heard these and then jumping back and up again. Could be a kind of a subharmonic thing happening, because normally what you have in a kind of a triggered module is that if the triggers become of too high a frequency, yeah, then it catches every other trigger. So it kind of has a point where it jumps back to a subharmonic of what you're inputting. So that can be a useful thing to know. But yeah, we could try to measure what is this maximum kind of triggering speed. Let's see if this works. I can, yep. So now I have, actually it's quite decent. So this is 1 millisecond, so this is now 1/10 of a millisecond per division. So I have less than 2/10 of a millisecond. Yeah, I have maybe 0.18 milliseconds. So yeah, come in. So that would be about 5K, I think. Or 50K, 5K, what is that? Anyone good with math like that? Because, yeah, it's 5 times more than 1000 hertz. Yeah? So that would be about 5K in terms of the frequency of triggering random values. Okay? Cool, so in terms of this, well actually this module, I'll talk about this later on as we get into more complex forms of noise. But for now, what we're after is this nice little signal. Okay, so that's the noise. Now, I'll just briefly go into what can we modulate with this, because currently we're just listening to this noise. But actually, what we might want to be doing instead is controlling oscillator with it. So it jumps up and down in frequency as we play. So here's my sine oscillator. Hopefully will talk to us in a minute. Sine oscillator. Okay. Right. So now I can use this noise to modulate the frequency. Okay. And if I decrease the frequency, you get a kind of a jumping up and down in frequency that follows that signal. That's your kind of quantized noise thing. And then obviously as I increase the frequency of this, you stop hearing the jump and it actually gets noisy.
Is this completely random in how it's the logic?
It is a random, yeah, it's a random generator like that, yeah? So that's one way we're going to be looking at what it does. And there are a few other things we can do. I'm probably not going to go into these. Maybe towards the end of the lesson if we have time left. But what I have here is obviously you can control the cutoff, the Q factor in terms of filter control modulation. You can control the timing of things. So if you remember what we did last time is we had a comparator on an envelope, and with that what we could do is essentially create a time delay for a trigger, because as the envelope drops, setting the level differently would make a different time delay, which means that by setting the threshold of comparator with such a signal, we could randomize an actual kind of rhythmical timing as well. Then the interesting thing, which I'm surprised people don't talk a lot about, whereas it's one of the easiest things to do, it is cross modulation. So you use a VCA, you just multiply with the noise signal. Yeah? Maybe this is something we could hear quickly. So I have put the VCA into the rack for today. So I'm gonna put a sine wave into my VCA, and then I'm gonna modulate the amplitude of that sine wave with my quantized noise signal. Okay, so this is currently just the sine wave, yeah? And then as I increase this, it's not very responsive, is it? See, that's my noise signal just in the CV input. But it doesn't do too much to my sine wave. The thing is that if it was a more complex sound source, normally it does more, but what we can do is just compare the two. So this is my original sawtooth wave, except I'm not monitoring that. Let's just get the other channel going as well. So who can tell me, what do you expect? You know the theory of sidebands. What do you expect from the spectrum if you multiply white noise, or for that matter something similar, with a sine wave? What do we expect from that?
Infinite amount of sidebands?
Yes. True. Anything else? I mean, we don't get the white noise through, so to speak. It does really depend on the rate of this, but let's see if. Oh, this is. Sorry, this is the. I'm just trying to get the second channel going as well, and be clever at the same time. Doesn't really work. Second channel is here, just so we see both. Okay, so this is now my sine wave, sorry, sawtooth wave. Let's see if that looks neat. Okay, let's change the trigger. Okay, so, well, it's a bit clipped, is it? So that goes again to my, oh yeah, that's the gain here. Okay, that's my unclipped sawtooth wave, okay? And then if I induce modulation with this noise, well, I mean, obviously I'm increasing the gain. I can make sure that I don't quite get to clipping. Okay, so let's start making sense. Right, and this is a very high frequency for my noise. If I reduce that, okay, so that's maybe another nice kind of modulation target to be looking at once we go through all the noises, in terms of, you know, getting this kind of percussive, you know, almost like little grains of sound happening. So you understand why this is happening. Obviously I have these jumps, and I'm increasing and decreasing the amplitude of the sawtooth wave in a rapid randomized fashion. Okay, so that's one target, and actually I have here the adaptive noise. So what we could do, I don't think we'll have the time, but it's an interesting thing to consider at least. What we could do is have adaptive, first of all, adaptive effects are the family of effects that use a certain analysis on the incoming signal, and that analysis is used to control the processing of that signal. So you could say that our compressor is an adaptive process because it changes the gain based on the amplitude of the signal. In a similar way, we could use noise in an amplitude-dependent fashion. Yeah, so we could actually do it both ways. We could say if the signal is above threshold in terms of amplitude, then we modulate it with noise, so we mess up the transients. Or we could say if it's below a threshold, we modulate it with noise, which would mean that the soft part of the signal, the sustain and the release of the signal, would be distorted and the transients would be clean. Yeah, so we could do these kind of things. And then obviously these are just the basic kind of modulation targets which are readily available in any system. I mean, for that matter, I have a compressor here which has the attack, release, makeup, threshold available as a CV modulation input. So as far as the modulation targets go, they're infinite. Yeah? Cool. So now we're going to look at the types of noise. What can we do with the noise signal? And I'm not going to, well, obviously, you know, in order to really appreciate the difference between these ideas, we're going to be listening to these noises in control signal domain. So we actually hear the going of up and down, so to speak. And most of these things will have slightly more subtle effect in audio range, but nevertheless they will have an effect. So never forget that, you know, the kind of transition between control frequencies and audible frequencies is our playground, really. Yeah, that's really exciting. Okay, so what we're gonna look at first, let's see, what's this? So I've briefly talked about white noise and colors, which I don't have available, and then the thing here is the quantized noise. And what we can do, first of all, with the quantized noise, I'm going to represent that quantized noise like this. The thing to understand about this noise is that I'm triggering it with an oscillator, so the time interval between each steps is supposed to be equal. So one of the things I can do to enhance the interest of this noise is to change the timing of my triggering. Yeah, let's try that first. Okay, so how do I do that? Well, what I have to do essentially is randomize again the oscillator itself. So in order to do this, well, actually, because I have only two oscillators, I can potentially, let me just have a thought. Now I'm going to be using these two oscillators. So we might be just listening to the noise itself. So I'm going to use one oscillator to, because I have two noise generators here, I'm going to use one oscillator to generate one type of noise. Okay, so this will be, this looks a bit like that. So that's my first noise generator of a fairly high frequency. And then I'm going to use that signal to control the frequency of the triggering. So just to check that that's happening, I can listen to this oscilloscope, this square wave first. Okay, so if I have no change of frequency, I get that, and then as I induce the frequency change, I get this. Now we're going to go into lower frequency ranges here. Let me see, what are we looking at? This should be on the second channel, okay? So here I have this square wave. Yeah? And then if I induce some randomization of that frequency, I mean, it was already there, it's a bit funny. Yeah, so that's the amount of difference I'm getting. So you can hear it, but the tricky thing right now is that, oh yeah, there you go. So you see now I'm triggering on the edge. So you see that this edge of my square wave here is fixed to the y-axis. So you see the rest kind of moving left and right. So that's the change in frequency, so to speak. Okay. Well, I would say that that's not huge as far as change in frequency goes. You see it's slightly wiggling. So if I would want to increase that, I'm pretty much at the edge of my, I think 1 volt per octave made, that's better. Okay, so I have two CV inputs for frequency on this oscillator. One where I can adjust the amount, and the 1 volt per octave input, which is a much more sensitive input as far as that goes. So now I'm changing the frequency of this square wave a bit more radically. And then if I go into lower frequencies, I actually see it's jumpy quite a lot. And then should be able to get the... Okay. It's a 7/8 beat. 1 2 3 1 2 3 4 1 2 3 1 2 3 4 1 2 3. It shouldn't be doing this, should it? Yes, I think I've actually messed something up, because this is the... What I'm doing here is I am controlling the... Let's see. Oh yeah, well this is... Okay, so this is just the triggering. But I would expect it to kind of be more irregular. I mean, at this stage, that's fairly irregular, yeah? And I hear the repetition. You hear the repetition as well?
It's like phrases.
Yeah, it's a bit like... Yeah, so there you go. It's not even... Oh yeah, I think it has to do with this distribution potentially. Let's see. That would... Again, it becomes periodic. Huh? But like this, it's fairly obvious that it's not really periodic. Okay, so what I was getting to is, now that I have a variable timing, kind of randomized timing of the triggers, now I can use this signal to generate noise as I did previously. So at this stage we should be getting something. Okay, so now I have the randomized timing and the randomized level. Without randomized timing, so you hear the kind of steady pitch coming through, and this is with randomized timing, a bit more beaty. Okay, so you understand this first concept, yeah? Randomized steps in terms of amplitude, and then randomized timing of these steps.
And the generate, sorry, just so I'm 100% clear, the triggers are being generated just by a random generator?
No, the triggers, so they're controlled. So actually maybe it's best if we draw this diagram, yeah? Let's get this one straight. So because I'm using two oscillators.
Yeah, I get that, but the thing that you're doing, what's coming from the yellow one, the yellow cable, what's that coming from?
So what I start with is this oscillator. You can come close if you're interested in the patch, yeah? So I start from one oscillator.
Yeah, I got that one.
Yeah, which is a pulse oscillator. Okay. And then what I do is I go into one. I have two triggered random generators. So I go into my first.
Yeah, that's what I was asking. So yeah, I've got the random.
I have two, yeah. So then I'll call it TR, triggered random. Yeah? And then this one goes into the frequency input of the next square generator. So that makes sure that it's moving in time, changing the frequency randomly.
This was the bit I did.
Yeah? And then this one goes into my second triggered random generator, which then produces the variable amplitudes. Yeah? So does that make sense?
Yeah, and this random generator, which was the question I was going to ask,
Yes.
is just an IC. It's just a pseudo random number. I mean, it's just generating random numbers.
We'd have to break it open.
Right,
You can look
okay.
it up online. I don't know what's behind it.
But it's
I
a
suspect
a unipolar.
I think it was unipolar. We can double check that.
Because if it's not, it probably is, and that's what I'm trying to work out. Yeah, we should check that.
It could be. Let's check if it's unipolar. I mean, in any case, I will talk about what, because they're actually slightly different.
So you've got you basically got two random generators.
One for the time and one for the
One for the
amplitude.
frequency
Yeah.
of the randomness.
Yeah.
And one for the amplitude.
Yes.
And the frequency one's being driven by the first oscillator.
Yeah, because obviously, because you see, that's the thing. So I have two pulses,
Running in
two
series.
squares. Yeah, all in series like this.
Yeah.
That's the current patch. So get a square wave to get an initial random number, and then that random number controls the frequency of this square wave, which means that the timing will change randomly. And then once I have a randomly changing trigger in time, I use that trigger to get a random amplitude, and that's what we were listening to.
And but what about the signal into the VCA? That's just the...
We just listened to this signal. There was no
we're
VCA.
only listening to that.
We just were listening.
Yeah.
So you notice that when I turned down the randomization of the time, you had a kind of frequency coming through, and when I induced it, then it was a kind of a meteor wider thing happening. Okay, so shall we check for the output of these signals? It's probably a good idea. I also like to sometimes unpatch everything just to keep the mess to the minimum. Okay, so let's just check for these. And actually, maybe it's a good time while we do that, I will also go into how these two triggered random generators are different. Okay, so let's examine these triggered random generators. This is my audio. I'm not gonna do that. I'm more interested in the oscilloscope. Okay.
So when you said, sorry, but they're the same unit, right? They're just
No, they're two different ones.
Oh, are they?
They have a slightly different function. Yes. Okay, so I'm gonna look at my first one is called quantized random voltages. And what this one does, well, let's first just trigger that, okay, at some frequency. Yeah, you see it happening. That's what's going on. As far as unipolar, yes, I don't see it go below the zero line at all. So the range is 0 volts to about 7 volts, seems. Yeah? So it is a unipolar. Okay, so, and then the other one, well, I actually have two inputs on this one, output, sorry. I'll talk about that in a second, same thing. And then this one as well, unipolar up to about 6-7 volts. Yeah, all four outputs. So I have 4 noise outputs and I have 2 clock inputs. It's actually 2 separate noise generators like that. They both need a clock. So without the square wave in there, it won't generate anything. It needs a trigger to give me a value. Now, the way it works is that the first one allows me to control the amount of different steps, which is really exciting because what I can do is I can reduce it to only 2 steps. You see, so the range is not huge now. What I can potentially do is go into a VCA. Actually, I've my most.
Is that essentially changing your bit depth?
Well, there is no processing of the signal. We will get into this.
When you talk about how many steps you've got.
Yeah, but it's not changing it because there's nothing to start with. We're not starting with a complex thing to reduce the bit depth. We're just creating a signal which has 2 values. You understand? It's a kind of brotherly process like that, but it's not bit depth change. We will talk about bit depth change. We need a different thing to do that. Okay? Yeah.
Right.
So I'm just going to increase the gain here, so we can see it. Or actually, I wouldn't even have to. Obviously, I'm a bit stupid because I have a nice oscilloscope that I can't really use, but I can do that on the oscilloscope as well. You see? So I have essentially 2 signal levels, and they are being randomly chosen. So what you see here is it seems like the frequency is changing, and this is an exciting point because it is not. The triggering frequency is still the same. The thing that is changing the thing that makes it so is the fact that it's choosing the same level one after the other, twice in a row.
That's the output from your random
Yes.
generator. So why is it always square? Because
Well,
it's
this
random.
one, now currently I have a setting called N, which stands for the number of voltage levels coming out of it. And now it's at its minimum, at which stage I have only 2 possible voltage levels that are chosen in terms of what's going on. But you see, that's the interesting thing, because actually this is a kind of a hack to get randomized timing already. Because you see, the fact that it's choosing the same voltage value twice in a row makes it not jump to the other one. So you see it neatly that you could use this as a randomized trigger. Yeah? Shall we try to hear that as a randomizing trigger? So what I'll do is I'll just stick it into an ADSR. Let's keep seeing it as well. Okay, so I'm gonna stick it into...
And can you put your clock in the other channel?
You want to see the clock? Yeah, sure. The clock is this one. Yeah? So see, the clock is a steady pulse, and then, well, obviously the triggering now won't help us much, but you see there it is. Probably best if I keep it on the second channel, yeah? So that's what's happening. So if we just want to hear this, I'm sending it into an envelope. Okay, attack, decay, sustain, release. And as you know, we can actually listen to the envelope. It really depends on the rate, whether we get more than just random impulses coming through. Okay. So now if I play with this frequency, you see I essentially get randomized things. Obviously the thing to understand is that it has what you could call a comp distribution. So one thing about random processes that we also consider is the distribution, which means the likelihood of different outcomes. Now what you have with analog white noise is that it's a continuous flat line, but with digital noise you actually get a kind of a comp pattern based on your bit depth, because you cannot choose a value in between, you know, your grid points. Yes, you actually have a given amount of possible outcomes. It's a discrete histogram essentially. Yeah, so these are the probability distribution function is the continuous counterpart of the histogram. Yeah, so the histogram tells you how often something happened.
But that depends on your random number generator, doesn't it?
Yeah, of course.
There's much better ones that give you much.
Yeah, of course, yeah, exactly. So what I'm saying is that in terms of the randomized rhythm, this is not a kind of a continuous distribution, because I have the underlying trigger. So the duration of each of these triggers can be only an integer multiple of the clock signal. Does that make sense? Okay, so yeah, that was my little randomized impulse created in a different fashion. And if I increase the rate here, I start to lose amplitude because it's an ADSR. Okay, that's a higher mode. The cones are still happy. I can actually make it a bit more subtle by getting the... So now I'm changing the parameters of the ADSR to get a slightly smoother waveform. Okay, so back to the number of triggers. So what you've seen here is, so let's get the ADSR out of the way here for the time being and just listen to this, okay? So now we're listening to the top signal. And now I can increase the number of steps that are being chosen. So there is now 3. I'm gonna have to what am I doing here? Oh yeah, this is that channel, and then here it is. So you see now I have 3 different voltages being chosen, and I can keep increasing this. Obviously I won't count it. It says it goes up to 6, but it starts at 1. And it's n plus 1, so it's 7. So now I'm supposed to have 7 different steps.
But it's still a function of the clock, right?
Yeah, so it's triggered by the clock.
But that's
Yeah.
kind of like the problem. It's always going to be square.
Always an integer value of
Yeah, exactly. Which seems to be the biggest problem you got.
Well, it's not a problem, it's a feature. And we'll get to different things. But as I said, my white noise generator just gave it up. So I don't have a way to give you a kind of a true white noise and play with that. But we can imagine what it does. Now, what I want to show you here is that obviously this is kind of a noisy thing. But what's really exciting is if I take this signal to control the frequency of an oscillator. Okay, so let's take a sine wave. Oops. Okay, so now I get 7 voltages picked randomly, so you get this kind of randomized arpeggio thing. And if I decrease the amount of steps, see now I have, what is this? Yeah, so I'm just now controlling the frequency of the sine wave with this noise. Here is the binary noise, yeah? 2 levels, 3 levels, 4 levels.
What scale are you do? Do you have the scale?
So yes, that would be the next kind of thing. So how could we control these intervals? Well, it's just about controlling the range of this signal. So what we can I have a sip, please? Yeah, no. I'm a bit thirsty. Too much talking. Good job. I should actually, on Wednesday is the last one. I promise I'll bring. There is this downside cider, and it's like a homebrew thing, really. And it has the most oak I've ever tasted in a cider. The barrels, because I have a friend who's a winemaker, and I know the room with the oak barrels is like, ooh, especially when he gets them fresh, because actually they lose value every year. And this cider is, I'm bringing it next Wednesday. Okay, so what we're dealing with here is this randomized noise signal. And we have 3 different steps. Let's just play with 3 steps for the sake of simplicity. So this is 1 potential value, 2nd, and the 3rd one. So as the random signal plays, I will get one or the other. I could have a clock which picks the same value, so this one lasts a bit longer, this lasts 1. You get the picture, yeah? So how would I control the actual pitches? Well, in terms of the offset, if I want a higher or a lower pitch, I have to add or subtract DC from the signal. And in terms of the interval, what is the distance in frequency?
From your,
I have to scale it.
From your oscillator signal going in.
So this is my random signal.
Yeah.
And if I scale it, I will change the pitch relationships. Yeah. And if I offset it, I will just change the overall kind of how high it is, the register, you could say. Okay, so let's just try doing that briefly. Okay, so I'm gonna now change the gain essentially of the control signal before it. Well, actually I could do it here as well, never mind, stupid me. Because you see, that's actually something that is quite important to understand. Just to do this first, but I will talk about this. You see, so now the interval is smaller. so I'm just scaling the signal so the difference in voltage is different. Okay, so one thing that is really important to understand, actually I was studying modular synthesis in The Hague at the Sonology, where they essentially have no factory built stuff. I mean, it's built kind of, obviously not by hand, everything, but it's all in-house designed, which means that they have a slightly different kind of niche to their stuff. And what they had is that none of the modules would allow you to scale and offset the input signals. Yeah, so they had the separate scaling and offsetting. So you're always aware of, okay, this is the raw signal that my module gives, I want to control the frequency, and there is no CV control on the frequency. Yeah? But what you actually have in kind of more commercial products is that a CV input, what it would do, it would have gain control for the CV. So you have a CV input and you can control, essentially it's an amplifier before the target. So I actually could do this kind of changing the frequency in the oscillator itself. I didn't have to use a separate multiplier. So a lot of this gear would have a multiplier ready for you before the CV input, and it would also have the offset, which is normally the actual dial that controls the value. Yeah? Let me just see if they close this door. Oh. Guys, just keep it closed and a bit down if possible. Yeah? Thanks. Yeah, so that's the message, that most of these inputs, without that being very explicit, do have an offset and a gain stage for the CV inputs. Yeah, so if I look now at this oscillator here, so my frequency CV control does the change of the gain there, and my actual frequency knob does the offset. Yeah? So very often when you think, okay, I need to season my signal, I need to scale and offset it, you might not need to use a separate module for that, because the CV input might already make that available. Is that cool? Any questions so far? Okay, so now we're going to try and design something based on a desired target. Well, let's think about it. I mean, I didn't have... I made this plan, this list of things in the morning, and I was like, okay, I'm going to prepare this well, you know, I'm going to go through all these, I'm going to draw the patches, actually I have a few drawn. But then I spent so much time with just messing about because I didn't realize my white noise generator was bad. So I was like pushing, it's like things are not happening, and then I, you know, realized that that was bad. And then the second thing that I actually realized, two of my modules had a problem. So I didn't get to try out all these techniques, but we can do it together. So this next idea, which I've called piecewise noise, would be such that we have a bottom line which is considered, well, actually it's not, well, we'll do it in a certain way just so you see. So what we're trying to do, we have this kind of stepwise noise, but what we had so far is that they were just kind of floating random steps. Yeah? So we get this melody happening, but there is no pause in the melody. Yeah? So what we are trying to do now is make sure that we have a zero line, and then we get these events, so to speak, happening with different values. Okay? We're going to try to do that now. Now, in order to achieve this, what I can do is I'm going to use a module that you haven't seen yet, I didn't explain it yet, which is max-min module. Yeah, I have a module in my rack, and what it does, it has 4 inputs, and what it will output is the maximum voltage of the 4 inputs. Yeah? On one side, and on the other side it will output the minimum voltage. Yeah? Okay, so how can we do this? And obviously what I'm trying to do here as well is be able to move this threshold. So if you imagine this original kind of noisy signal, whatever it is, and I want to get this kind of bottom line to it, I also want to be able to move that bottom line. Because if I move it up, I will digest, I will kind of remove more of the signal, and the higher I move it, the less triggers I will have. You see, if this kind of threshold line is fairly high up, then I expect only a few things to pop through. Yeah? And if I have it all the way down, then I expect a more dramatic thing. So in essence, what I'm about to hopefully control is a certain density of events, of randomized events with this technique. Okay? So let's see if we can get that working. So first of all, let's make sure. So this is now, we are still triggering. We won't have to look at the trigger signal now, okay? So this is my noise. I have now a few steps. Worth saying is that my two inputs on this randomization where I control the amount of steps, I have two outputs. One is n+1, so it goes from 2 to 7 different voltages. And the other output is 2 to the power of n. So actually it goes from 2 to the 2 to the power of 7, which is how many? Well, 7 bits. Yeah? So I get a 7-bit noise signal from this output, potentially. So I do have a kind of a way to get much more discrete voltages out of this. Okay, and you see it here. You see this output will give me visible distribution of steps, and this output actually looks much more random like that. Okay, so I will use this output, right? And then take this into my maximum minimum module. And now the thing is that here what I have is I have only one input activated. So on the output signal we get the same thing. Because the other inputs are at 0 volt. And this signal is always positive, so it will never be kind of capped from below. Okay, so in order to cap it from below, what I need to do is put a DC signal into one of the inputs. You see, and now if I increase this DC signal, so now I'm probably somewhere above, well, I can probably even read it. Now I'm actually at 5 volts almost. You see, now I get only the bits that come above 5 volts. Okay? And then if I really want this type of signal, what I need to do is I need to offset it back such that I move this signal all the way down so that this actually becomes the 0 line again. So if I want to control the frequency like that, so I'm going to attempt to do that here, no influence there, and then this is okay. So let's look at that signal. So yeah, so now I'm offsetting that signal as well, and I can make sure it goes down to the 0 line. Well, that's actually the maximum gain I have seemingly for now. Okay, and now I can say, well, this is now the signal that can be used just straight into my sine wave oscillator, such that I get silence, hopefully. Oh, it seems like I'm getting much more than I bid for. Let's see, I have another one of these available. So the top is the original signal, we don't have to watch that right now. cable. Okay. But what I'm interested in is this signal, which is controlling the sine wave frequency. Okay, so we see it's actually above the 0 line. But you see I have a kind of a bipolar CV input here, because if I go below, it is still a kind of a, if I have a negative CV into the frequency, it is still audible. So I'm not quite getting the silence. But what I could do now, and maybe that's an interesting thing, so I'm still up for trying to get kind of randomized events rather than just kind of a randomized frequency, yeah? So how could I, now that I know that my CV input is bipolar, it doesn't allow me to make silence at 0 volts, essentially, yeah? How would I achieve that effect otherwise? Any ideas? You've got a few? I'll take this one then.
Yeah, you take that. Yeah. I've got another 2 left here, and I'm picking some on the way out. So
okay, so how would I achieve it that I do get silence between these randomized events? I do have a kind of density control, which is obviously, you know, on top of, just a second, on top of the fact that I'm controlling the trigger frequency. So with the trigger frequency, I also control the density. So it's a kind of a dual thing. Yeah. So.
you could use a gate on
Well, I can just use this signal that reaches to 0 in my VCA. Yeah. So I actually am using the same control signal for the frequency and the amplitude. Yeah? And when it drops to 0, then I can hopefully get a situation where I don't get the sound out of it. Okay, and now I have to just figure out that bit. So I have this randomized thing, and this is my essentially clipped noise. Yeah, we're clipping it from the bottom, and then I want to use that clipping from the bottom in a gain stage. Okay, and instead of listening just to the plain sine wave, I'm gonna listen to that, and let's get that through in here. Okay, so now if I well, it looks like it's still not quite silencing it the way I would like to. Let's just see what's going on. So I'm gonna scope the actual output, what we were just seeing. You see, and it's actually not CV input. So for some reason my CV is the, oh yeah, I've done the wrong thing. This is the input. So this is my CV signal. So it's still quite positive. How am I doing this? Just a second. That's the output of that in there. Okay. So, and the first. Okay, so this would be my threshold. I'm getting into a fairly complex thing here. Kind of losing it. Because I have two scaling and offsetting. Okay, here we go. Yeah? So we get a kind of a changing of the amplitude in there as well. Okay, so this is the offset, this would be the gain. So if we listen to that, potentially higher frequency. See, so I'm changing the amplitude of the signal as well. Yeah, with the same signal that is changing the frequency. Okay? What's the time? You guys feel like a break, or shall we just get on with it? It is 8:15. A little break will do as well. I might need one. Okay, so how about you guys in the meanwhile try to sketch this patch? Yeah? Go for a piss. Yeah, so see if you can make a data flow block diagram which does this. So let me just repeat what we're doing. So we're having a noise, quantized noise. What we're doing with the min-max module is we are pushing the lower clipping level up such that only the tops of this noise come through and the bottom is clipped. Then we're offsetting this back such that the bottom of the clipping level is 0. And then we use this signal to control the frequency of the oscillator and the amplitude such that it drops back to silence. I didn't quite get it to be audible like that, but that's the idea, yeah? So grab a pen, grab a paper, give yourself a few minutes and try to sketch this, and then we'll look at it together. Or just go for a piss, fag, go to the offie.
Thank you very much.
Yeah, go for it, no?
Interesting.
Yeah, did you manage to follow a bit?
No, I've messed around with them, but
It's high level, yeah?
Yeah,
Yeah,
it's still
exactly.
interesting, definitely.
Cool, yeah,
Thank you,
sure,
have a nice
take
day.
care now. I think it was a random passerby.
Yeah, just like,
Probably.
we'll have a look.
It's fine.
So I'm interested. So I tried it. I got a wobble bug.
All right, cool.
Yeah, which does the same thing,
Mhm.
thing. And so I attached that. I was trying to generate some noise to go on top of the kick. And so I was like, oh, I'm going to do this. And so I have a DPO.
Okay.
You know, I've just borrowed it. It's nice to buy. Just borrowed it. You know, which is the West Coast maintenance.
Yeah, yeah.
So what, and that has a folding in it. So what I did was I took the wobble bug into both it has two oscillators on it. One's just
Right.
a standard, you know, sine wave or whatever.
Yeah, yeah, yeah.
So I took into the sine wave on that one, and then into the oscillator that you can fold, and I turned everything. I turned the FM all the way up, I turned the folding all the way up,
Yeah.
and I got the wobble bug to trigger it, and that gave a white noise.
All right.
Yeah, because it was effectively.
Yeah, exactly.
And actually, it was quite a nice white noise.
Yeah,
But
yeah.
that, and my guess is that's working just because it's frequency modulating it across the whole
Yeah,
thing.
yeah,
So it's
I
doing a
mean,
very similar thing.
Technically,
Then the folding
if
gives it the because it was only when I folded it
Yeah.
max that it really became
yeah, well,
interesting.
well, you see, I mean, technically, if you input white noise into the CV of an oscillator, you get white noise. You know, because it's not because white noise has this.
I was doing it into the one octave, you know, the one octave. Is that what you mean?
Yeah, if you
Yeah,
control the
it's a-
frequency of an oscillator with
as well,
pure
so
white
You
noise,
should get it.
you should get
Yeah.
white noise, really. I mean, it depends on many other factors, but that's technically the case if you do it digitally. Because you see, if you think about a digital system and you change the frequency of the oscillator
Right, so I can
every
see how
sample
in digital
value,
it would work, everything
it
would
is a
work.
bit like
That's
making
how-
a random value
Yeah.
for every sample anyway. So that should work. I mean, what you would get, you see, because the difference between white noise and pink noise is that the pink noise has a relationship to the previous states in a way that it can deviate by a limited amount from the previous state. So if you think about this sine oscillator controlled by white noise, you could say, well, actually the phase of the sine oscillator is somewhat more continuous than plain random. So you might not get that many high frequencies,
Yeah.
but it's as good as noise, really. I mean, you've heard here, you know, I managed to run it up to 16K. Now, what you also heard is that I got this subharmonic series coming up when I increased the triggering frequency, and earlier today I figured it was about 3K, the top limit in terms of, you know, steps. I can get 3,000 steps per second and not more. So even if I drive the control signal higher, the triggering signal, I would still get only about 3K, which is a funny thing because I have this other module which is an offset and gain with a slew rate limiting, and that also kind of caps at 3K. I think it might have to do with the type of chip that they're using, or it's something inside there. Okay, so you all have lovely graphs, I see, prepared, yeah? Never mind. Okay, so we got this. I call this a kind of a piecewise or kind of event randomization. And we have a few more. So the next one up that I have is curvy.
You can draw it up then.
What could I?
You can draw it up. You'll see.
Oh yeah, shall I draw it up? Yeah, let's do it. Sorry.
You can see it. So it's much
Please remind me. I'm like, yeah, you're not even interested, yeah? So, what is the circuit here? I've tried to remove this line, but it doesn't really work. Well, you can see it, yeah, it does work. Okay, so what we said, what do we have here? So we first of all have a trigger signal. That should be a square wave, yeah? Then we have the triggered random generator. This one then goes to my minimum module, whereby the other input is a DC voltage that I control with a single dial. Yeah? So this is my mechanism where I can push up the lower clipping level. Then to this I add another DC voltage, which is negative, to get it back to reach the zero line. And then this signal goes into an oscillator and into a VCA. And this oscillator goes into the VCA, and that's my output signal. Make sense? Here, for the viewers at home. Okay? So that's that. Okay, so the next one up is curvy. So we've seen these stepwise things, but actually even before curvy I should go a bit into the... Actually that's what I meant by piecewise. It's just that I had a different thought and I wanted to do that as well. Because I think in Max MSP the piecewise envelope is the one that essentially has linear interpolation between random points, or between specified points in that case. So what I'm thinking of now is a kind of, we still have random values which are normally controlled in terms of how frequently we get them, this kind of quantized noise idea. But instead of a stepwise signal, what we're after now is essentially a connection of these points with a linear kind of interpolation thing. That's a kind of a triangle noise, you might call it, okay? So how do we do that? You guys know it already? We use... Huh? Well, actually, if you remember last time I looked at this ADSR, and what we figured is that it will have some amplitude dependence. But the problem with the envelope that it will go through all these stages. It doesn't really follow the signal like that. It is more of a triggered thing. So it would consider each jump potentially to be a trigger to the extent that it crosses the threshold line. Whereas in this case you want to go point to point, exactly. Okay, so any other ideas? So let's get back to our stepwise thing first, okay? Hello. So this is my stepwise signal, okay? So what I need to do is I need to lag it. Lagging, slew limiting is interchangeable set of terms. Okay, so, and if I now look at that signal, there's another splitter. Splitter, this is a long one. Okay, so on top I expect to see my random signal. Is that happening? Pulse here. Did that suddenly stop happening? Oh yeah, of course. Clock. Okay, so that's my stepwise signal. And now if I take it through slew limiter, what I hope to get is a kind of an interpolation between the things. So I increase the time, the slew time, and you see that's what's happening. So I get a kind of a smoother transition between these steps. Huh?
Like low pass filtering.
Yeah, it is like low pass filtering. That's a very good remark. And it's not because you gave me the cider. Okay, so let's now just kind of listen to when we control a sine oscillator with this. You see, this is the kind of interpolated, and I decrease the slew time.
That's banging.
So from this, by increasing the slew time, so you first hear kind of a portamento thing, that you get a glide between the notes. And if I increase it sufficiently, that's my kind of continuous random signal. Okay?
Captain Scarlet.
So next one up is a different slew limiter. So actually in this case what I have is a slew limiter which has a single time-based control. So in terms of the rising flank, the dropping flank, it is limited in the same extent, to the same extent. And I have a different one here which has both up and rise control on different pots, which allows me to create a kind of an asymmetrical glide. Yeah? So what that would mean is if my release time is large and attack time is short, it means when I go up to the next note it will jump immediately, but if the next pitch is lower, then it will glide. So I get a kind of this asymmetrical glide. See, so now it's jumping up and gliding down. And now it should be the other way around. Is that traceable? Maybe the easiest way to trace this is if we go back to two values in terms of our random signal. Okay, so here is my binary random signal. Yeah, only two values. So without any lag, you just get these jumps. Now increase the attack time. Happening. Now you see that the attack is, I can change the range here to mid. Okay. And then if I increase the release time, you see it jumps faster and it drops slower. That's the kind of thing I can do. And then finally, I have a third slew limiter here as well, which is the one that actually does funny things. Worth noting about this one, actually we'll talk about slew limiters in a second, maybe not. So this third one, what it allows me to do is actually control the curvature of this as well. So I can control the rise and decay times. And I found that if I control the curvature with a DC signal, I get a lot of joy. So now what's technically happening, the lower signal is the one that we hear in terms of frequency, yeah? We get a kind of curvature. So the point here is that I'm not changing the time of the glide, I'm just changing the curvature of the glide. This can be an interesting thing. I typically got this module for synthesizing drums. You see, because what you can do is obviously take this kind of a square wave into an oscillator through the slew limiter. So you get a kind of punk kind of sound, and then you could more precisely control the frequency drop. So it doesn't have to be linear, and in terms of the curvature, you can even control the kind of depth of the curve as such, which allows you to get into this detail of how a kick really sounds, because it's a very short transient with a very large drop, so that makes sense. Okay, briefly about this, I'll just try it briefly for joy's sake, because I managed it before noon, and in the afternoon I couldn't quite get it to do the same thing. That's what you get sometimes, because this more complex slew limiter, what it did, which was very cool, it also generated subharmonics, you see, because what it did is when the ramp was not finished, then it did not take the next trigger. Yeah, so it actually forces the finishing. It has a priority in terms of first the ramp has to finish, and then I'll look further, which means again that it would be skipping triggers and thereby making a lower frequency, making a subharmonic generator. Okay, so let's get the pulse. First, let's get it just into a basic lag, just a single time constant. Okay, so are we seeing this on the scope? So that should be my. Okay, so now I've skipped the randomizing. I just have a square wave, and I have this lag control, and then as I increase the lag, increase the slew limiting, you see I get a kind of a smoother thing. And then what you also see at some point, in this case, I'm starting to lose amplitude. Yeah, because in this case what you have is that there is a priority to the next trigger. So let's hear this, hopefully. Okay, a bit less. Okay. Okay. So this is currently my signal, and then as I increase the frequency, I lose a bit of amplitude. But it actually neatly goes all the way up. Yeah? Hello, Sam. All good, all good. Okay, so no anomalies there. So you see, actually it acts a bit like a low-pass filter, yeah, what you've noticed. Now, to be more precise, it acts a bit like a low-pass gate. So we haven't talked about those yet, but low-pass gates have one thing in common normally, is that as they remove the low frequency, they actually end up with silence. As the filter comes down in frequency, the amplitude comes down as well. So it is a kind of a process that relates more to the, to the gradient of the signal, because if you start limiting the gradient, which is something that we do here, as you keep limiting, the amplitude of the signal goes down as well. Yeah? Was that a question, smack of lips, or was it?
When you say low pass gate, are you like brick walling below a certain frequency?
It's just a different way to do filtering, because essentially what you have is that, people spend a lot of energy and time to make a filter which has an accurate frequency control and which has a kind of a reliable amplitude transfer. That's the thing, because as you're changing the cutoff frequency, what you expect is that the range of frequencies, certain range of frequencies, should not be affected. You see, if I move my filter between 1K and 500 Hertz, I don't expect that the energy at 100 Hertz should change at all. But this is technically not trivial. I mean, it's easy for us to explain and to think of and to imagine, and digitally it's not even that hard, but as far as I understand, in electronic circuits, this is a problematic thing. Yeah? So, and this is what a low-pass gate is. It's a kind of a non-kosher kind of a filter with an anomaly in essence, because it acts also as a VCA. That's why I have these people talking about, okay, so it's a low-pass gate, it's a bit like VCA and a thing. So as you decrease the frequency, you decrease the volume as well. That's the kind of thing that happens in a low-pass gate.
Right, okay.
And that's why they call it gate, because it kind of gates out the signal. Huh?
Like a two-stage.
Yeah, but the point is that it's not a combination of the two. It is a single design which has this property.
Just has the.
It just does this.
Just does these things.
It just does, and they're inseparable like that.
By design, or just as
well, by lack of design, you could say.
By lack of design.
Yeah, because
It's smoother though, right? It must be smoother because it's doing the gradient.
it's just a different thing. But I think, in a way, the reason why it works really well musically is because the amount of high frequency actually tells us about the intensity of the sound source. It's a very kind of important psychoacoustic phenomenon, the intensity, and it's not trivial. It's not just the amplitude, it's not just the power of the signal. It has a lot to do with the timbre as well. So you see, if I play a whispering voice really loud, you still understand that the intensity of the sound is low, it's a whispering. And if I play a really soft screaming voice, you still understand that it's screaming. And what we have with electronic sound sources is that if we mess this up, then they start to become more kind of alien, non-real, non-acoustic things. We recognize this as a character because there is no true relationship between intensity and the volume, which is the case with an acoustic sound source. Yeah? And this is what you get typically obvious, because we kind of are used to these.
But that's kind of a psychoacoustic.
Synthetic, yeah, it's a psychoacoustic thing. And it normally comes forth really obviously if you have a mixture of acoustic instruments and synthesized things. And then you understand that, when you mix a gig like this, then like, wait a minute, why does the electronics not blend? It doesn't have the depth, it just doesn't work. But if you actually make sure that in your electronic sound sources the intensity is linked to timbre and amplitude, then you lose this problem. And that's why low-pass gate is good.
What you get with the
exactly.
Gate. Right,
yeah, so actually it kind of links.
I never knew the difference to this day. That's really interesting.
Yeah, that's a really important aspect of creating a kind of acoustic-y electronic sound.
Right.
Obviously, if that is your.
And the low-pass gate is the low-pass gate is the West Coast. Stuff like that.
Yeah, supposedly, there is a cultural background to this as well. It just means they're shit designers, is it? It's not bothered with making
too much weed, right?
Yeah. Was that back in the day as well? Probably San Fran and all these places.
Yeah, exactly.
Because now it's
That's where it
legal
came
as
from,
well.
wasn't it? That's where it came from, that, whatever it was.
Yeah.
All those synths out there.
Yeah, exactly, yeah. Bukla is from
Yeah.
West Coast, yeah?
When they,
Okay, right, so we've looked at these lag networks. Oh yeah, so now we've looked at this one. Did we lose the sound? Oh yeah, it's the frequency. Is that it? Okay, so this one, as I increase the frequency, this lag network doesn't do much. If I take the other one, which has attack and release control, you also don't hear it do horribly interesting things. It's a bit like controlling the cutoff and the amplitude at the same time. But what this exponential slew limiter does, it can actually freak out. And I've managed to get it to do this earlier. And then the second time around I didn't quite get it. And that's why I actually developed a little patch. I can show you this one. This is the only thing she's liking it or she's not liking it?
Mad, I reckon.
Yeah? That's alright. So I've developed just a little kind of funny patch you may want to see, and I'll patch it in a second. It's this one. So what I have here is a square wave into the slew limiter, and then hearing that as a sine wave oscillator. Okay. Yeah, so let's do that. So I'm taking the output of that. I'm not listening to it anymore, but taking it to a frequency there.
I was going to ask you if you ever implemented chaos.
Oh, this is the only thing I do. This is everything outside of this I do with Modular is looking for intermittency and chaos. And the problem is that I find it all too soon. That's why this is really useful for me as well, because I'm being more analytically creative rather than okay, let's find it.
Yeah.
It's like, okay, what does this do? What does that do? Okay, so this is now. So you see, actually I get this thing happening already. So now I have only the black thing running. I don't even have the feedback loop yet. So I have a square wave into my exponential slew limiter. Then that controls the frequency of the sine wave.
Where are you introducing the intermittence? Is it with the DC?
It's not happening yet. But what I have here is that if my slew is too large, then I get it to kind of lose tracking of the frequency, yeah? Because you see, if I managed to get something really interesting there earlier. Okay, and then what I had is a feedback loop whereby I took the actual sine wave output, as you can see it on the sketch, and feed it into the CV input of the and you see already I get nice little intermittency going on. That's the thing where the science kind of stops for me. There are ways to analyze nonlinear dynamics. It's rather complex. As far as I'm concerned, it all has to do with growth, a gain factor, and a limitation. And if the growth is too large, then the limitation throws it back. And initially it's an oscillation, but if the growth is far too large, then you get a kind of a chaotic, noisy thing happening. That's what happens. Cool. How are we with time?
20 minutes.
20 minutes, good. Okay, so we've looked at this. We've looked at n steps noise. Yeah, so I could control the amount of different steps. But what I also have here is a way to control the distribution. Yeah, so believe it or not, it's a module so that's the second half of my triggered random. So the first top half allow me to control the amount of steps that are coming out, and the second half allows me to control the distribution of the steps, which means the likelihood of steps. Okay? So let's listen to this just by checking this sine oscillator. Okay, so we're gonna listen to that sine oscillator, and I also want to display the actual control signal. So we're gonna do that as well. Okay, so if I'm here bang in the middle, then what I have is that the distribution is middle heavy, so to speak. So I get much more values in the middle than at the extremities. Let's see if that's okay. So I'm not sure how is your musical memory like that. Oops, sorry. That just got two things. Guys, can you keep it down? It's really loud. Okay, so supposedly here I have more often a frequency in the middle. If I turn this distribution left, then what I get is much more frequently a low value than the other values. You hear it? So I'm sticking in the low voltages, and if I turn it full right, I get much more high voltages, and only occasionally I get a low voltage. Yeah? It's important to understand that for while this is happening, the range of voltages is not changing. So I still have a chance to reach the lowest and the highest value. It is just that the chance itself is being changed. Yeah? The probability of different outcomes, the distribution, likelihood of different outcomes, any way you like it. Okay? So that's another way of controlling my noise. Okay? And then what I have as well is melodic quantization. Okay? Of noise, it is fairly widely used. So what I have, well, first of all, I could let's make this noise lagged a bit. Okay? So I'm just going to take it through my lag stage before that with this cable. Okay? And then that into the CV of the sine wave, just to hear that back again. Okay, is that producing something? Okay, I unplugged it, that doesn't help. Okay, so it's the same thing. Let's take a bottom heavy distribution, yeah? And I can introduce some lag. Which will make it, well actually if we look at it like this, you can probably see, you have lower values occur much more frequently, and then occasionally jumps up. And I've introduced some lag here. I kind of lose the steps because I'm sort of interpolating between these points. Okay, and now that I have this signal, what I can do is put it into my melodic quantizer. Okay, so here, and the output of that into my, and for this to work I would need a 1 volt per octave input, which is actually tricky now. Okay. Actually, I might have to change this around because I want to trigger it from here, and I want to, let's take this back, because I need the 1 volt per octave input to actually get the pitch accuracy that this technique allows for. And then I listen to this sine wave. So what I have here is actually a way to say, okay, I'm going to do a major scale. Yeah? I can have a chord, put a quint in there. Okay, I can have a minor scale, and I can actually even have the 4th interval in there. I can have the 7th. I have the 6th instead as well. Okay, so just we can produce noise which will then fit into a melodic scale through this kind of melodic quantization. Yeah, this is a fairly widely used technique, by the way, in modular. Okay. Then I'll just mention this because I didn't put my sloth into this rack. There is a little hype around the sloth generator, which is the slowest. It gives you really slow noise. So typically it would, you know, you can leave it running for 2-3 days and it keeps changing very slowly, like very minute changes, which is actually fun, you know. If you, sometimes in performance or just while patching, I would put it in one of the CVs just for fun, because, you know, and even when you leave the whole thing alone, it would just keep changing.
Just adds a touch, right?
Yeah, just a small variation which is continuously happening. It's quite interesting because you understand that this kind of noise randomization is the basis of generative systems.
So it's probably quite nice to use something like that in a musical situation where if you have too much randomization, it becomes confusion.
Yeah.
A small bit, it's interesting.
Yeah, it's always like this. I mean, if you look at, so as far as the spectral profiles of noise are concerned, what you have is that with white noise, if you would to use it for any old musical process, what you would normally find is that it's too random. Because if you have a range of values, essentially with white noise, the case is that you jump from one value to any other possible value each time, which is just uncorrelated noise for us. It doesn't really make any musical sense. Now, if you have brown noise, which is a limited step away from the previous step, then perceptually you often get a sensation that it's too predictable. Because you kind of know, oh, it's going to go up or down by about this much every time. And pink noise is in between these two in its spectral profile. So you understand that white noise is flat and then the brown noise has a lot of low frequency, and the pink noise is in between the two. And actually the way to synthesize pink noise, one of the simple algorithms, if you don't go into this computer science holy grail, how do we make the best pink noise, one of the simplest ways to do it's a Voss generator, Voss, I think it's a Dutch guy, and what he does is he produces basic noise fluctuations at different timescales. So what you get is an interesting little scheme, and that's the really musical one. That's why I'm saying this, because if you actually analyze things like Mozart's music or something like that, you know, just analyze the notes and look at the profile in terms of statistics, then you get mostly kind of a pink noise spectral character. And the way this Voss generator works to make this pink noise, so you don't go small steps, it's not brown, you don't go completely random, but what you do is you take completely random steps, you take white noise on different time scales. So I would take it on like a small time scale, whatever that is, then I would take it slightly longer time scale, slightly longer.
Just like inspiration.
No. For now it's just stepwise signals. It is just that they are of different time scale, even larger time scale, and so on. This is supposed to be regular triggers. I'm a bit messy here. And then you add everything up.
Okay.
Which makes it such that you have large fluctuations occasionally, and then within that you have some detail. So it's a bit like repeating the melody in different register.
But it has frequency, it has different spectral components.
Exactly, and this kind of algorithm will give you pink noise, which is in between the white and the brown noise.
Right, yeah.
And this is the musical thing. Actually, if I do this, well, I have two random generators. We can try it. It's an interesting thing to say, okay, I'm going to run one at a low rate. I'm going to run one at a higher rate. I'm going to add them together. So I get a kind of a long-term change and a short-term change. You see, that's the thing, because with the brown noise and the white noise, in a way, there is no development. You see, they very quickly become obviously static processes. You just understand, oh, well, it's just doing that thing randomly, and it never kind of stretches its own boundaries. But with this technique, what you actually get is that the boundaries are occasionally completely moved. Suddenly I'm playing in the high register, suddenly in the middle, and so forth. So that's the kind of musical background of the pink noise. Okay.
So these sets, when you see people doing the generative stuff you're talking about, they're often using the Turing machine going into a quantizer.
Mhm.
That's effectively what you're talking about here.
Yeah,
I'm
exactly.
assuming the Turing machine is basically a random.
Yeah. It has a few things to it, but
generate
yeah,
sequences.
essentially it's a kind of a sequence randomizer
And
as
then
well.
they put that, and then they seem to put it into a quantizer, like you say, so they.
Yeah, so you get a
scale
kind
or
of a
whatever.
melodic thing
Yeah,
going
exactly.
out. Yeah, definitely.
That makes sense.
You're actually making me think, could we build a rhythmical quantizer like that? Well, I don't know, if we go for a drink after, maybe we can think about it collectively. But what I want to finish with is something a bit more exciting, potentially. So you see, we didn't get into all the modulation targets, but we're almost at the end of my list for the noise types. And the last thing I have is what did I actually think? Because I didn't draw down this patch. I say interrelated to noises and logic. So I'll start patching it, and then hopefully I'll realize what I really meant with this.
Is that kind of not what you were just talking about?
No, because so far we've actually dealt with a single noise source or kind of a noise source controlling the other one when we got the randomization of time and amplitude.
No, what I meant was what we were talking about here.
It might be actually. We could probably get something like that going on.
It's like different types
Yeah.
of noise and putting them
Let's try this and then we'll expand to logic. That's a good idea. The only thing is that I won't have a way to. Yeah, I can cycle this one. I can get a kind of.
I've got to go today.
Oh yeah, all right.
Because we're going to, it's 5 to 9, I'm going to the cinema at 9:30, so
All right, don't miss that.
we're going to see Black Panther, so I'll see you.
Nice for coming. Wednesday is our last class for the course, intermediate.
Oh,
So
okay.
come along on Wednesday.
Yeah, definitely come on Wednesday.
And then in March, well, actually we'll talk with Marco about that. I don't know if he sold a few more tickets. We might be running it at UE. We'll figure it out. We'll run it anyway.
Either's fun for me.
I'll let you know. So we'll have a few weeks break before that.
Well, I'll see you on Wednesday anyway.
Okay, cool.
Alright, cheers, thanks.
Anytime. Okay, so now we're gonna do this combination of two noises at different rates to finish off. So what I have here first of all is a basic, this should be a fairly slow rate thing happening. You see it there being drawn. Okay. Yeah. So, and then the amount of steps increases as well. Let's just take that back. Oops, sorry. Okay, so we have this slow pace noise. You see it happening, okay? And then what I will do is I will also have a faster pace noise in the other channel. Clock in there. Looks a bit like this. What is happening here? Oh, I've increased the sensitivity a bit too much. Okay, so we have a slow noise in one channel, we have a fast noise in the second channel. And then what I suggested is that if we mix these two signals, we will get a more kind of musical thing, because we will have the combination of the two. So let's look at that, and let's drive a sine wave oscillator with the sum of the two. Okay, so here is my sine oscillator, and then let's listen to that as well. Okay. So my, oh sorry, this is the scope. So we're scoping it and we're listening with this cable. You see? So I can now change. See, so you get a kind of musicality. It's not strictly random, it's not strictly boring. And then what we can also do, which is fun, is run this through different logic gates. Okay? So what I have here is an AND gate. So there is a certain threshold to this. Now it's happening only occasionally when both signals are yes. So you see, essentially this logic module takes in voltages and considers them either on or off.
So
it's a binary thing, yeah?
And or.
Yeah.
Exclusive and exclusive or.
Yeah, exactly. So I have an AND here, that was this. Well, the signal level is a bit low. And then I have the OR. Yeah. But actually that was, it's so funny, I can't remember what I meant with interrelated to noises and logic. But anyway, we've heard this kind of multiple scales of triggering, which, as you heard, you know, it does suddenly something more kind of musical, more a sense of developing stuff. Right, shall we call it a day? We're bang on time, it's 40 seconds to 9. So with that, thanks for coming, guys, and see you on Wednesday, I hope. Cool. Oh, thank you.